can continue, right? So you remember in the previous lecture, we started looking at the example where we started applying, actually almost applied Gauss's law, one of the fundamental laws in physics, right? So we decided to look at sphere uniformly charged, right? So uniformly charged sphere of radius r, and the total charge is Q capital. Total charge is uniformly distributed over the whole sphere, right? So in part A, we decided to find the electric field outside of the sphere, right? Okay, so we decided to use Gauss's law, and of course, as the first step, of course, we have to pick a Gaussian surface. Okay, we picked one. Of course, it must be in the region where you want to find the electric field, so we picked it, right, of some arbitrary radius r. And after that, we started applying Gauss's law, right? So first, I decided to evaluate the flux, the electric flux through this Gaussian surface. You remember, this is an imaginary Gaussian surface, right? All right, so we identify directions of the electric field, area vector, right? And at all points on the Gaussian surface, they are parallel. So we wrote down explicitly the expression for the dot product, scalar product, and we ended up with integral of product of magnitudes, E and dA, right? So then we use the symmetry of the problem. So since electric field should be obviously constant at any point of the Gaussian surface, again, magnitude of the electric field, so we could extract it from the integral. And as a result, we ended up with this, right? Again, this integration is not that trivial, but of course we know the answer from high school, right? So the answer is the area of the Gaussian surface, so 4 pi r squared. Right. So, and of course, so we plug it back over here, and as a result, we ended up with this adjusted Gauss's law, right, for this particular situation. So on this side we have flux, and on this side we have Q enclosed divided by epsilon naught. So that's where we stopped in the previous lecture. And now, of course, the next question is usually find the enclosed charge. And warning you about very typical mistake at this point. For example, on the exam, I ask students find Q enclosed, and what maybe like 30% of students, what do? They just solve this equation for Q enclosed. So they just write Q enclosed in terms of E. It's not wrong, but it's useless because you're writing unknown in terms of another unknown. Right? So which doesn't give you anything. So our final goal is find electric field. So now the goal is we need to find Q enclosed using some other reasoning, some other arguments. Using, I don't know, density, charge density, or total charge, looking at the picture, right? So don't do that, don't just solve Q enclosed in terms of electric field, because it's just useless. Right? Again, I would never say it's wrong, it just doesn't give us anything. Right? Okay, so now let's find Q enclosed. And again, you remember Q enclosed, it's a total amount of charge physically embraced by the Gaussian surface. In our case, Gaussian surface outside of our sphere, what's the total charge embraced by the Gaussian surface? Of course, the total sphere, the total charge Q, because the whole charge is inside of the Gaussian surface. And again, you remember, distribution of charges doesn't matter for the Gauss's law. It doesn't matter if the charge is over here or there, right? As long as the charge is inside of the Gaussian surface, just count it in towards the final value of Q enclosed. So in this case, finding Q enclosed is trivial. Total charge is inside, right? So I can write, so Q enclosed equals to Q. Right. Okay, so now you just plug it, of course, into that, and we're getting the almost the final expression which we needed. So let me rewrite it. 4 pi r squared E equals to Q over epsilon naught. I just drop the subscript, right? And now we can solve it for E, because now Q is given, R it's a variable, epsilon naught is the constant, so we can write electric field as a function of R equals, this goes downstairs, it will be Q over 4 pi epsilon naught, and okay, these are constants, and then times 1 over R squared. And of course, we must add that this is correct for the outside. When you are outside of this sphere. So that's the answer. That's the expression for the electric field outside. Right. Actually, probably I should have wrote Q over here above this R squared, but these are just cosmetic changes. Okay, so that's how you can apply Gauss's law to find electric field outside of the charged sphere. Now let's find inside. Right, let me think. I think I mentioned everything. Yeah. So now it's a part A, now part B. So we need to find electric field inside. So when R is less or equal than R capital. And again, we will use Gauss's law, right? Okay, let me rewrite it. So E dot dA, Q enclosed over epsilon naught. And again, the first step must be, we need to pick a Gaussian surface. Right, and again, first of all, a Gaussian surface must be in the region where you want to find electric field. Again, it's another very typical mistakes. Very often on the exam, I ask students to find, for example, electric field inside, and then I start walking around the classroom, and lots of students just pick Gaussian surface outside. Just be careful, right? Read the problem carefully. And then I have to warn everyone, guys, I'm asking you for the electric field inside, not outside. So of course, after that, students usually change position of the Gaussian surface. So be careful at this point. All right, so first Gaussian surface, and since we're interested in the electric field, so I prepared this picture in advance, right? So we need to pick a Gaussian surface inside. And again, you can pick any shape of the Gaussian surface, but we must be smart and pick the best surface so that we can use all these symmetries. So obviously that here the Gaussian surface must be a sphere concentric with the this charged sphere. Right, so let me draw slightly distorted. Not so slightly. Right. Okay. Of some arbitrary radius r small. So that's our Gaussian surface. Okay, maybe I will write. So that's our Gaussian surface, right? Okay. And now, of course, I'm going to evaluate this flux, right? E dot dA, and now I will write all these steps up to this point here are going to be exactly the same. Not a single symbol is going to look differently, or order of those symbols going to be different. Exactly the same things, right? So of course, first I will find directions of dA, right? So this will be direction of dA for, for example, or here direction of dA. Electric field will be still radial. I can give you exactly the same justifications, right? So this will be electric field, or over here, this will be electric field. So all those steps are going to be exactly the same. So I will just write exactly the same steps as in part A, right? So immediately I will write this, the value of the flux. 4 pi r squared times E. right? And then, of course, from the other side, that flux must be equal to Q enclosed over epsilon naught. So, right. And so now the question is, we need to find Q enclosed. So here, finding Q enclosed is a little bit more challenging, and based on my experience, I know maybe like 60% of students usually make a mistake over at this point. If I give something on the exam similar to this, right? Okay, let me try to explain. So I'm going to sort of do it using two approaches, but they're barely different. Basically, they're potato, right? That's how they are different, right? But anyway, and of course, we need to recall that slide, what, 2 lectures ago, about when we spent like 10-15 minutes discussing charge densities, linear, surface, and then volume charge densities, right? You remember we had three boxes, and now we need to apply the last box, the third box, where we discussed volume charge density. Now, all those formulas we need here. And students usually making a mess with those formulas. Okay, first, let's find volume charge density. Okay, maybe I will write first that rho, it's a volume, and then I will start finding it over there. Volume charge density. It's a three-dimensional case because we have three-dimensional charge distribution. So how can we find volume charge density? Because it's not given. It's the formula number 1 from that slide in the third box. So you know that the total charge Q is distributed in this volume. So how can we find density? Simple. You just take the total charge divided by the total volume, right? It's like if I want to find, let's say, my density, I will take my total mass and divide that by my total volume. So that will be my mass density. Here, charge density. The idea is the same. Just change mass with charge. So it will be Q divided by the volume of the sphere with radius R. Right. Okay, so of course we're talking about this, right? A volume of the sphere with radius R, of course, it's a 4 pi over 3 R to the power of 3. So that's volume charge density. And so usually the next step, I of course use the formula number 2 in that box number 3 from that lecture. So it will be Q enclosed. And you know what? Of course, first of all, we need to see on the picture where Q enclosed. I see. Yeah, guys, somebody's mic is on because now I see you started chatting a lot, right? Somebody's, please turn your mic off. And okay, it looks like you're discussing charge density. Okay, I cannot, guys, cannot read the chat and discuss it. Doesn't work, right? All right. If you have questions, just ask it, right? So yeah, first of all, let's see where Q enclosed is, because it's essential. So this is our Gaussian surface. So Q enclosed, it's all the charge physically embraced by the Gaussian surface. So of course, we're talking about charge which is in this sphere, right? So that's where Q enclosed is. Of course, it must be smaller than Q capital, because Q capital total charge is distributed over the whole sphere, but our Gaussian surface now is smaller. So of course, Q enclosed is going to be smaller than Q capital. All right. So now, how can we find that Q enclosed? It's a formula number 2 from that box number 3 from that lecture. right? So we need to take the volume charge density and multiply it by the volume of this Gaussian surface. It's like let's say once I found my mass density, and now let's say I want to find the mass of my hand. So how can I do that? I need to take the density and multiply by the volume of my hand, and that will give me the mass of my hand. Exactly the same story here. Again, usually students don't have troubles understanding mass density, but once we switch to charge density, and lots of misunderstanding and wrong results. So we need to multiply it by the volume of the sphere with radius r small, which is basically the volume of the Gaussian surface. So of course I can write it, I can plug rho here, right? So it will be q divided by 4 pi over 3 r to the power of 3. So that's rho. And volume of the Gaussian surface, it's a 4 pi over 3 times r small to the power of 3. Right? So 4 pi over 3 gets cancelled, and we're getting what we needed. So q enclosed will be equal what? Q, right? So that q, and the ratio of r small to the power of 3 divided r capital to the power of 3. Okay, let me frame it, because again, as I said, maybe like 60% of students at this point write something which is not correct, usually on the exam. Okay, I also noticed that some students accept better a different, slightly different explanation. Okay, let me give you, it's basically the same, right? But slightly different, presented in a slightly different way, and I noticed that some students kind of, wow, it's better for them. Okay, let me write or, right, or. Okay, we just found surface charge density. Let me get some water. We just found this charge density using the total charge, 4 pi over 3 r to the power of 3, right? So I just rewrote this. How else can we find volume charge density? So over here we use the total charge, which is distributed over the sphere with radius r capital. But we can write similar because we have uniform charge distribution. So the charge density is exactly the same at any point. It's a constant basically for this object charge density. So can we use Q enclosed to write down also the volume charge density? Of course. But of course now we will have to take Q enclosed and divide it by the volume of the Gaussian surface. Gaussian surface. So we can also write as Q enclosed over 4 pi over 3 times r small to the power of 3. Right? So you can use either total charge to find charge density, volume charge density, or you can use Q enclosed, which is over here, and divided by the volume where that charge is distributed. And of course, these are the same, right? Because we have uniform charge density. And of course, if you compare, of course, these two guys, of course, you will end up with exactly the same expression for Q enclosed, right? Of course, you will end up with Q enclosed will be total charge Q and divided by the square, cubes of those radii, right? Again, some students prefer this, they like it more. Some students like that. I usually use that, right? Although I have nothing against this, right? It's also nice. Again, potato, potato. Right, okay, practice it. In the lecture, which I'm going to post today, right? There also will be an example with a hole inside of this sphere, charge sphere, right? You can look it by yourself, right? After getting the idea, then any small modifications, it just increases complexity, but not that much. Okay, so now what? We need to go back to this because we just spent like what 10 minutes discussing Q and close. So now we need to go back to this. All right. Okay, maybe I will write something like this. All right. So moving. All right. So it will be 4 pi r squared small times e equals, and instead of Q enclosed, that again, guys, somebody's mic is on. All right. Write epsilon over there. Yeah. Okay, now let's simplify it. This r to the power of 2 and that gets cancelled, so we'll have only r to the power of 1, so just r. And so now let's solve it for the electric field, and now of course it will be a function of r. Kind of getting a feeling that something is missing. No, so far I don't see any troubles, but I have a feeling that something is. No, it's good. All right, so it will be q over 4 pi epsilon naught r to the power of 3. All right, so these are a bunch of constants for this particular problem. Let me put brackets, and then times r. Right. And again, that's for r less or equal than r capital. Okay, let me check just in case. No, of course it's correct. Of course it's correct. So that's inside. Outside over here, outside electric field decays as 1 over r squared. Inside, it's growing as 1 over r. And of course, electric field at the center of the sphere is 0. Of course, maximum at the surface. Actually, we can plot it. Actually, let's plot it before I forgot it, right? So I will put a new bullet. And now let's plot electric field versus r. Magnitude of the electric field. Direction is radial. Okay, and let's say this is r capital. So inside, it's some constant, and function is over there, linear. So it grows linearly up to this point. And of course, this electric field at the surface when r equals to r capital and the value of this function at the surface, they match, right? They match. You can check quickly, right? All right, and then outside it decays as 1 over r. All right, so here electric field is proportional to r, over here is proportional to 1 over r squared. So that's how electric field changes with r around uniformly charged sphere. So application of Gauss's law. So in our recitation classes, we practiced cylindrical symmetry. Just in my recitation classes, like quarter of the problem left. I will discuss it tomorrow, right, in my recitation classes. You also discussed in your recitation classes, and in the lecture we discussed spherical symmetry. Right? Definitely on the first exam, midterm exam, there will be one of the problems will be about Gauss's law, either spherical symmetry or cylindrical symmetry. And of course, as a result, no, not as a result. As I told you in the notes, there will be another example with a hole in the center, concentric hole in this sphere. Right? So look also at that example, just to practice. Right? And again, as I said, it's not a rocket science. After a couple of times, it's everything is quite straightforward. All right. Okay. Now, if you don't have any serious objections, then I will cover it with screen and we'll switch to the presentation, right? And a new material. Okay, so let me turn on this is the example which we just discussed, right? And this is the plot which I just plotted, right? So now, new material. Oh, I need to press these slides. Right. So, new material. Now we can say, okay, we are experts in Gauss's law, so now we know how to apply it for in a different situations, right? So we know all the properties of the Gauss's law, and now, of course, we will start applying it everywhere it's possible, right? It's sort of like a if you give a kid scissors, right, then everything in the house will be cut in pieces, right? So we are pretty much in a similar situation, right? So now we have a new tool, and of course we're going to stick it everywhere it's possible, right? Okay, and we're going to use Gauss's law today a lot to explore properties of conductors. We need them. We need them a lot. Of course, in the electrostatic equilibrium. Of course, we will define all that in a second, right? Okay, it's still chapter 24. The code is here, you see, 5144. All right, don't forget to enter it before the end of the class. And so, first of all, we need to discuss the major difference between insulators or dielectrics and conductors. So I prepared these two pictures. First, let's start with a dielectric material. You see some kind of bulk dielectric material in insulator, right? And we're going to use sort of like a classical model of an atom, right? So inside we have you see that a red dot, basically here a bunch of atoms, and at the center you see a red dot, which represents red dots, which represent nuclei, right? And then around, for example, this red dot, we have what? We have electrons orbiting, right? Which are represented by those green circles, right? So the first dark green represents core electrons. What does it mean, core electrons? Just the electrons which are closer to the nucleus, right? Core electrons. And then light green valence electrons, which are reasonably far away from the nucleus. So in an insulating material, all those electrons are tightly bound to the nuclei. So it's very difficult to strip them away, to get for them to get loose, right? Most likely, if you apply, for example, very large electric field, most likely you will just damage the material. But right, we're not discussing damaging situation. So most likely you will just distort those atoms, but electrons will be still belong to nuclei. Right. So as a result, all this space, you see, all this space between atoms, is empty, and that is a very gigantic space relative to the sizes of atoms. So there are no free electrons in insulators. So all electrons are all electrons belong to nuclei, right? Sort of like imprisoned, no free people over there, right? Now, what about metals? In metals situation is different. So these valence electrons, right, those which are reasonably far away from nuclei, those valence electrons are weakly connected to nuclei. As a result, for example, if you just increase the temperature of a metal, right, I was just started searching for something which is metallic, but there's no point of showing you metals. You all know metals, right? Aluminum, gold, copper, tungsten, molybdenum, right, and so on. If you just even slightly increase the temperature from absolute zero, tons of those free electrons will get loose and fill all that space between atoms we create, okay, yeah, there will be tons, as a result, tons of free electrons. Even if you just sneeze probably on that piece of metal, right, some additional electrons will get loose, right, and a number of free electrons will be increased. So the major difference between insulators and metals, that metals have tons of free electrons. And now if you, for example, apply some electric field or apply potential difference, of course, electrons in metals, they will start drifting in a certain direction, flying in a certain direction, giving us electric current. But if you do the same in an insulator, all the electrons are tightly connected, right? And so it's almost impossible to create an electric current, right? So the major difference, metals have tons of free electrons. And now, based on that fact, attendance code, come on guys, it's visible, right? So, and again, if you don't see the total screen, right click on the video and fit the screen or something like this. Every time I keep forgetting, right? It just, I know, sometimes by default, Microsoft Teams crop part of image, right? Okay, so now based on this result, we should be able to add additional properties of conductors. Okay, so now let's do it. So let's start with a piece of a conductor. Again, piece of metal. And let's assume it's an electrically neutral. Right, so what does it mean electrically neutral? It doesn't mean that it doesn't have charges at all. No, it doesn't mean that. It means that it has equal amount of positive and negative charges. So as a result, overall, it's electrically neutral. So it has tons of electrons inside and of course, tons of positive charges. Okay, and now, right, I'm just looking at the chat. What do we need to do with the attendance code? Okay, probably something new, right? Yeah, I see somebody posted a link. Yeah, just need to go there and enter the code. I described it in the course policy. So now let's expose this conductor to some external electric field. Let's, for simplicity, assume it's a uniform electric field, right? Okay, and now what will be response of the conductor if we expose it to this uniform electric field? Of course, over there are tons of, because it's a conductor, it's a piece of metal, right? All right, so for example, over here, there's an electron. So what does this electron do when it starts feeling this electric field? Of course, it will start experiencing electric force. F equals QE, charge times the electric field. All right? And of course, since electron is a negatively charged object, of course, the force will be pointing that way in the opposite direction. So, of course, electrons will start drifting this way. And of course, it cannot pass this border. Of course, the electrons are going to accumulate themselves over here near this surface, leaving behind, of course, positive charges. Right? So let me, something like this. And now the question is, how many electrons are going to move over here? 100, thousands, all of them. Basically, the question is even not about how many electrons, but about the stopping mechanism. From the point of view of physics, right? What is the stopping mechanism? At which conditions, at which the electrons will stop drifting to this side? And the explanation is this, right? So, look, now we have here negative charges, they're positive charges. Do they resemble anything to you, this distribution of charges?
Does it look like polarized?
It looks, yeah, of course it's polarized. Yeah, it's a fancy word. We polarize the material, right? But in simple words, we can say it looks like we have a capacitor, right? So negatively charged surface, right? Positively charged surface, and of course these charges, these blue charges, of course they're going to create their own electric field, blue electric field, internal electric field. So on top of this external electric field, red, which we drew using red lines, now we're going to create, okay, charges, create blue field. And of course, pointing in the opposite direction, because again, you remember electric field lines from plus to minus. So now inside of this conductor, we have two battling fields, blue and red. Sort of like, again, colors, right? It's like a Republican and Democratic representation, right? Fighting to each other, right? Here internally, right? So, and now let's see, let's analyze. So what electrons do, again, as we discussed, right? So let's assume that first 100 electrons move to this side of this conductor, right? And they created some small internal electric field, so some small blue electric field, right? So we have strong external electric field, and first, let's say we have small blue electric field in the opposite direction. Of course, the net electric field is going to point still that way. The external electric field wins, right? And the net electric field will be pointing this way. And of course, the electrons are going to feel that net electric field, right? And of course, they will still drift that way, right? So, of course, electrons drift, and this blue electric field becomes stronger, but still smaller than the red one. And of course, the net electric field is still not zero. Still will be pointing that way, and electrons are going to feel that. Of course, they're going to feel electric force, and again, they will keep moving to this side, right, where the negative charges. So, and they will keep doing, electrons will keep doing this until what? Until the net electric field inside of the conductor becomes zero. So at that moment, this blue electric field in magnitude becomes equals to that red external electric field in magnitude. At that moment, electric field, the net electric field inside of the conductor becomes zero. And now electrons, of course, will stop running. They will stop moving, because if there is no electric field, of course, the electric force will be zero, and there is no reason for electron to travel, to drift. So pretty much at that moment, at the moment when electric field, internal electric field equals to the external electric field, when the net electric field becomes zero, at that moment electrons stop running. They stop running, because there is no reason. They stop running, they get settled, and buy a house, get married, and live happily ever after, right? So at this moment, when the net electric field inside of the conductor is zero, and electrons stop running, so these conditions are called, we can say now that a conductor is in the electrostatic equilibrium. Right. So pretty much all these discussions was about to say that in the electrostatic equilibrium, electric field inside of the conductor must be zero. So electrons will keep running and running and running until they will make electric field zero. They will never stop running if the electric field is not zero, because in that case they would feel electric force and they will be pushed. So they will keep running until the electric field inside of the conductor is zero, right? And at the moment when they achieve that, right, the electric field is zero, they stop running, and now we can say, okay, now our conductor, our piece of metal, is in the electrostatic equilibrium. So from now on, most of the time, our conductors are going to be in the electrostatic equilibrium. And today, of course, in all our discussions, we're going to use that. Conductor will be in the electrostatic equilibrium. Right, okay, so that's again, it's not a proof, it's more like a justification explanation, right, of this important fact. The electric field inside of the conductor will be zero in the electrostatic equilibrium. So now What about, okay, in the previous slide, the conductor was neutral, electrically neutral. Now let's charge it. Let's charge it. For example, with positive charges, right? Have a positive attitude, right? Use positive symbols. All right, so let's assume that we have, for example, this piece of a conductor, some arbitrary shaped, right? And let's assume that it's charged. And of course, now the question is logical, more or less logical. Where does this excess charge, so it's charged, so we're talking about the excess charge. So where does this excess charge reside in the conductor? It's a logical question. At some point, sooner or later, right, if you were a researcher 200 years ago, you would start asking yourself the same question. So let's answer that question. And guess which law we're going to use to answer this question? Gauss's law. As I told you, now we're going to use Gauss's law a lot. And of course, you remember, Gauss's law can be applied at any point of the universe, at any moment of time, for any Gaussian surface, right? So it doesn't have any restrictions. So we can apply it here. And of course, let me pick, since I can pick any Gaussian surface, so my soul desires at this particular moment to pick the Gaussian surface, which is just below the surface of a conductor. You see this greenish line just below the surface of a conductor. And again, the key word, just below the surface of a conductor. Of course, I exaggerated, right? I left that gap significant. Okay, so, and now Gauss's law. So let's apply it. Electric field, electric flux over this Gaussian surface, right, equals Q enclosed over epsilon naught. Anyone, do you see what will be the value of this integral? What will be the value of the electric flux? And again, this conductor is in the electrostatic equilibrium, as I told you in the previous slide. So now we're going to use that condition almost all the time. The value of this integral is 0. Why? Because where is the Gaussian surface? The Gaussian surface is, it's below the surface, barely below, but still it is inside of the conductor. And in the previous slide, we just discussed that inside of the conductor, the net electric field must be 0. Otherwise, electrons will never stop running. So, since the electric field inside of the conductor is 0, so we're just integrating over the surface, and the value of the function, the value of the electric field is 0 at every point. So of course the electric flux will be 0. So this is 0. As a result, so if the left-hand side is 0, then of course the right-hand side must be 0, right? So Q enclosed, it means must be 0. Q enclosed must be 0. It means what? It means that inside of this Gaussian surface, right, inside of the Gaussian surface, it's impossible to have an excess charge. So if it's impossible to have inside of the conductor, then where else can it be? Of course, on the surface, because that's the only place in this conductor left outside of the Gaussian surface, because we position our Gaussian surface just below the surface of a conductor. So, conclusion, if you have a charged conductor, positively or negatively, right, all the time the excess charge will be on the surface, of the conductor. In simple words, because okay, we proved using Gauss's law, universal law, blah blah. In simple words, if you, for example, dump some positive charges at this point in the conductor, right? So you remember what like charges do to each other. They hate each other, they push each other, right? And they run away from each other as far as possible. Of course, they will try to run away as far as possible from each other. And of course, the sort of farthest points at the surface. So of course they will reach the surface and without being able to move any further, right? In simple words, but of course that's the proof, right? So in the electrostatic equilibrium, any excess charge must reside on the surface. In this case, this exterior surface. Right? Okay, so that's the conclusion. So now in the electrostatic equilibrium, electric field inside 0, and any excess charge must reside on the surface of the conductor. right? So now, what's next? Electric field outside of the conductor. Electric field outside of the conductor. I'm going to use sort of like a proof by contradiction. At least this book uses that. All right. And of course, in this situation, again, we're going to assume that the conductor is in the electrostatic equilibrium. And of course, the conductor must be charged, right? Why? Because if the conductor is not charged, then the electric field outside of the conductor will be zero, right? So there wouldn't be anything to discuss. So that's why let's assume again that conductor is positively charged. And the question is, what can we say about the electric field outside of the conductor? And electric field outside of the conductor is perpendicular to the surface all the time, right? Perpendicular. And during the normal semesters, students, when they do their first lab, normal lab, right, they map electric field, and usually there is some kind of electrode, and they map electric field around the electrode. And of course, if they do it properly, they would see that the electric field outside of that electrode, electric field lines are perpendicular to the surface of that electrode, because the electrode is made of metal. Right. Okay, so electric field outside is perpendicular. Proof. Again, we're going to assume that it's in electrostatic equilibrium. Proof by contradiction. Let's assume that there is a tangential electric field, right? By contradiction. Let's assume, what if there is an electric field tangential to the surface? So if there is a tangential electric field, of course, the electrons inside will start feeling, will feel that electric field. They will feel electric force as a result. And of course, as a result, they will start running around this surface. They start running, but it's impossible in the electrostatic equilibrium, right? You remember, we assume that this conductor is in the electrostatic equilibrium. And if we assume that there is a tangential component, electrons start running, which is impossible in the electrostatic equilibrium. If electrons are still running, it means the conductor hasn't reached an electrostatic equilibrium. Of course, yeah, in the real life, if you just take a piece of a conductor and shoved it into the electric field, of course, you will have to wait maybe for nanosecond, maybe for microsecond, right? You have to wait, of course, for some short time until the electrons redistribute themselves, right? Until they stop running, until they manage to make an electric field inside zero. It takes time, a little bit of time. So every time we're going to assume that we waited that short period of time, and now conductor is in the electrostatic equilibrium. Right? Okay, so it's impossible to have tangential electric field. As a result, so what's left? Only perpendicular. So electric field outside of the conductor is perpendicular to the surface all the time. Again, in the electrostatic equilibrium. Before that moment, of course, everything is possible, right? It's a mess. It's a mess inside of the conductor. Right. Okay, so that's just in the words the proof. All right. Okay, so next. Of course, next, what's the expression for the electric field, magnitude of the electric field outside of the conductor? We're not going to do it. A couple of times I did it, and then I decided to stop it. Right. So you will just need to remember that electric field just outside of the conductor is surface charge density. Right. Charge density on the surface of the conductor, right? And divided by epsilon naught. I think one of your homework problems will be about this formula, right? So there will be some coin, there will be electric field will be given, and you will have to find some information about the charge. But it's just the direct application of this formula, that's it, right? Okay, so this question we will discuss on Thursday. Right, probably there are some additional properties of conductors which I haven't managed to discuss today. I will probably ask our recitation instructors to cover that, and of course I will cover in my recitation classes. There are like additional 3 properties. Right.